Not all questions can be labeled as the legend. However, the one I'm about to show you can be. It was from the 1988 IMO question number 6. Only 11 people in recorded history have been able to get this exam question correct. I myself have been trying to solve this question, but after 3 months, I finally gave up. But luckily, I finally found a solution that I was able to follow, and I'm going to demonstrate that to you right here. So the question was, let a and b be positive integers such that a squared plus b squared over ab plus 1 is equal to k, for k is some positive integer. If k is a positive integer, show that it has to be a perfect square, or PS for short. So how do we do this? Well, first of all, you should be able to recognize that this is actually a very good question. I'm going to try to explain to you what this question is asking, because that's what you need to understand, right? So let me give you an example. If a is equal to 8 and b equals 2, then what we get is 8 squared plus 2 squared is over 8 times 2 plus 1 is equal to 68 over 17, which is 4, and this is a perfect square. If a equals 1 and b equals 1, what you get is 1 squared plus 1 squared over 1 times 1 plus 1 is equal to 2 over 2. This is 1, which is also a perfect square. Now, if a equals 3 and b equals 2, you get 3 squared plus 2 squared over 3 times 2 plus 1, which is 13 over 7. This is not a perfect square, but at the same time, this is not a positive integer, so we can just ignore it. So, how are we going to prove that every time k is a positive integer, it has to be a perfect square? Well, the way we're going to do it is by contradiction, or an indirect proof, if you will. So, what we're going to do for this particular question is we're going to let k be a positive integer, but let's assume that it's not a perfect square. So let's write that down. Answer. Okay. A proof by contradiction. Assume k is a positive integer, but not a perfect square. Now, whenever you have solution sets like this for a and b, you always have a smallest possible solution set. So let a1 and b1 be the smallest solution set to this equation. Next, notice that the value k has a symmetric equation. This means that k of AB is equal to k of BA. So, like, earlier we found out that if A was equal to 8 and B was equal to 2, you got a value of 4. But if we were to swap this and say A equals 2 and B was equal to 8, we would also get a value of 4. And this is not coincidental. Let me show you why. Because on the numerator, a squared plus b squared is also equal to b squared plus a squared. And in the denominator, ab plus 1 is equal to ba plus 1. So the order really doesn't matter. So as a result, We can say WLOG without loss of generality. Suppose A1 is greater than or equal to B1. And the order really doesn't matter. We could say B1 is greater than or equal to A1 and we'll achieve the same result in the end. So let's suppose A1 is bigger than or equal to B1. Let's plug this into our original equation now. And let's swap this equation around a bit. Let's move everything to one side to make the other side 0. So we have a1 squared plus b1 squared. Let's multiply both sides by a1 b1 plus 1, which is equal to kb1 a1 plus k. And we can say that a1 squared minus kb1a1 plus b1 squared minus k is equal to 0. From this, we can say that a1 is a solution to the quadratic equation x squared minus kb1x plus b1 squared minus k is equal to 0. So, as you know, this is a quadratic equation, and a quadratic equation has two solutions. A1 is the first solution. Let's call the second solution A2. So, we can say that A1 and A2 are solutions to the quadratic equation. This quadratic equation right here. And as you learned from grade 10 math, this means we can factor this equation into x minus a1 times x minus a2 is equal to 0. And when you expand this out, you get x squared minus a1 plus a2x plus a1 a2 is equal to 0. These two equations represent the same thing. These two equations are exactly the same thing. So by comparison, what we have here is, when you compare these coefficients, you have a1 plus a2 is equal to kb1. And when you isolate a2, you have a2 is equal to kb1 minus a1. Here, we also have a1, a2 is equal to b1 squared minus k, which then means when you isolate it, you get a2 is equal to b1 squared minus k over a1. Now let's do some comparison. So, for our first equation, a2 can no longer be a decimal. You know why? Because k, b1, and a1 are all positive integers. When you add, subtract, and multiply integers together, your end result has to be an integer. K, b1, and a1 are all integers, so a2 has to be an integer. Next, we have a2 is equal to b1 squared minus k over a1. And based on this equation, a2 cannot be 0. You know why? Because remember our assumption, our very big assumption in the beginning. We assumed k is not a perfect square. So because k is not a perfect square, that means k can never be equal to b1 squared. So as a result, our numerator value b1 squared minus k can never be equal to 0. And there's also one final clue. Let's plug a2 into our original equation right here. let's plug a2 right here. We have a2 squared plus b1 squared over a2b1 plus 1 is equal to k. Well, from what we can see here by analysis, a2 squared plus b1 squared is positive. And also, k is positive. So this means the denominator value, a2b1 plus 1, has to be positive as well. But based on that information, a2 can no longer be negative. Because if a2 is negative, then it's not possible for a2b1 plus 1 to be positive. So based on these 3 points of information, a2 has to be an integer, a2 can't be 0, and a2 can't be negative. We can conclude that a2 has to be a positive integer. So we deduced that a2 is a positive integer. Let's go back to our original claim, a1 is bigger than or equal to b1. So let's, remember how we said that? Let's go back to that. So a1 is bigger than or equal to b1. I'm going to square both sides, and because a1 and b1 are positive values, the inequality will still hold. So what you then have is a1 squared is greater than or equal to b1 squared. From this, we can say that a1 squared is strictly greater than b1 squared minus k, and divide both sides by a1. When you do that, you get a1 is greater than b1 squared minus k over a1. And we found out earlier that this is equal to a2. So we now have shown that a1 is greater than a2. But this is a contradiction. We said that a1 is supposed to be the smallest. Yet we found that a2 is less than a1. This means our original assumption about k was wrong. That k cannot be a perfect square when it's a positive integer, that assumption was wrong. So therefore, we conclude that if a and b are positive integers, and a squared plus b squared over ab plus 1 is equal to k, and k is a positive integer, k is a perfect square.